All right, SL, this is our chance to go over some of these problems that we missed as a result of the assembly. Let's see how it works. Okay, so this is question number 1 in the packet, multiple choice. Use the average bond enthalpies to calculate the enthalpy change in kilojoules for the following reaction. Okay, it's going to be bonds broken minus bonds formed. So you're breaking 1 HH and 1 H2. So let's add these together. And that should give us, let's see, 590. That's the energy you have to put in. And then minus 2 times this bond because there's 2 of them. So that's minus 600. And so you end up with minus 10. And your answer is C. Okay, so with bond enthalpies, it's always bonds broken minus bonds formed. Okay, which equation represents the bond enthalpy for that bond? The definition is you're breaking 1 mole of that bond and everything is in the gas phase. Gas phase, it shows the H and the B are separated. Everything is in the gas phase. The answer is going to be A. You don't reform any bonds and it can't be in the liquid phase. And there we go. The answer is A. Number 3, what are the units for specific heat capacity? Well, the C value is kilojoules per kilogram per Kelvin. And it's off the screen right now, but I think the answer has got to be D because I don't see an answer there that works. Yep, kilojoules per kilogram per Kelvin. The answer is D. Question 4. Given the enthalpy change for this reaction, which statement is correct? So it's a question to see if you understand the definition of standard enthalpy change of combustion or enthalpy change of formation. Okay? All right, well, it looks like we are doing, you could define this thing 2 ways. Either it's 2 times the delta H combustion of hydrogen, or it's 2 times the delta H formation of water. They can overlap sometimes, but a combustion looks at 1 mole of a reactant being combusted, and a formation looks at 1 mole of a product being formed. So in order to actually get their values, you would have to divide this value by 2. And that gives you negative 286. So first off, the last 2 are wrong because this equation shows 2 moles of hydrogen and 2 moles of water. And so this can't be right because the actual values have to be half as much. They have to be per 1 mole. So it's also not going to be positive 286 because the value here is negative, and we're just going to half it. So actually, the only one that makes sense based on the numbers is A, standard enthalpy of combustion of hydrogen. Moving on to 5, best definition of standard state. So a standard state is 298 Kelvin and 100 kilopascals. So first off, these are wrong because they say 298 degrees Celsius. A, the standard state of a solid is the most pure form of the solid. That sounds kind of vague and not like an IB definition. And D, the standard state of a gas is the most pure form of the gas at a pressure of 100 kilopascals. The fact that they've included the correct standard pressure means that D is a better answer than A. Okay, if we move on to question 6, this is a Hess's law question. Okay, you're going to have to use the simultaneous equations to solve this. All right, we've got, let me see if I can get it all on the screen at once. Okay, I'm trying to add up to this end equation. So I go through one piece at a time. I need 2 carbons on the left. Right now I have 1 carbon on the left in this equation. So I'm going to multiply this equation by 2. Which means multiplying this by 2. And so I get negative 2x is the enthalpy change for that one. So the carbon is taken care of. I need 3 hydrogens on the left. I currently have 1 on the left. So multiply this equation by 3 and multiply the enthalpy change by 3. So I get minus 3y as the enthalpy change I'm going to care about there. And I need 1 C2H6 on the right. I currently have 1 on the left. So I need to flip this equation, which means reversing it, timesing it by minus 1. And that means I get positive Z. So if I add up these 3 enthalpy changes, I will get the delta H for that final equation. So now the last issue is trying to find the answer that says that. That's a little tricky. But I have, let's see, a minus 2x, that works, a minus 3y, and a minus makes it a plus z. C is correct. These ones are wrong based on numbers, and this last one is wrong based on signs. It's got this positive and this part negative, so that's wrong. The answer is C. Is it? Can I go forward? Let's see. All right, question 7. So you're mixing things, and they want to know about the temperature change produced in this experiment. So notice the difference here is 50 cm cubed 1 molar, 50 cm cubed 1 molar. That's the same. This is 50 cm cubed 1 molar. This is 100 cm cubed 1 molar. Okay, this is a rather tricky question, but it really comes down to the fact that in both of them, the moles of NaOH are the same. N equals N. And in this one, you're using twice as much HCl, so you're going to have 2 times the moles of HCl. But because this reaction is 1-to-1, the moles of NaOH are still going to limit you. So having 2 times the moles of HCl actually doesn't do anything because you're still limited by the amount of NaOH. So all that we have in the second scenario then is we have twice as much water to heat up. And as a result, both of these reactions should release the same amount of heat because we've got the same limiting reactant, same enthalpy change per mole. So we're releasing the same amount of heat, but since we have twice as much water to heat up, we're going to have a smaller delta T in this example over here. Now, this is a very tricky question because it relies on you knowing that the reaction for NaOH and HCl is 1-to-1, and to figure out some limiting reagent stuff along the way. But you could maybe reason out just with the more volume over here, right? It's a lot more stuff to heat up. The temperature change shouldn't be as high unless you also have more moles to back it up. So the highest recorded temperature in A is lower than B. Nope. The highest recorded temperature of both is equal. Nope. The heat produced in experiment A is lower than the heat produced. Nope. And the heat produced in both is equal. Now, that was sneaky because they didn't even ask you about delta T. In both of them, because you have the same limiting reagent, same amount of moles of NaOH, the amount of heat released in both will be the same. That's a rather tricky question, but that's the reasoning behind it. Okay, question 8. This is also quite a challenging question because of the way they've chosen to set it up. I find it a little bit obnoxious. So you've got 1 gram of sodium hydroxide. You add it to 99 grams of water. On paper 1, look out for easy numbers to do math with. If you have 1 and 99, that gives you a total mass of 100 grams. You should be preparing for Q equals mc delta T. And it says the specific heat capacity is this, which expression gives the heat evolved in kilojoules per mole. So the Q is going to give me kilojoules, and the delta H is going to be the Q per N, per mole, right? Or the negative Q per N. So we've got negative mc delta T over N. So this big M on top is going to be 100 because I'm heating up 1 gram sodium hydroxide plus 99 of water. The temperature goes from 18 to 20.5. So if I'm filling in the pieces here, this is going to be 2.5 for the temp change. Specific heat capacity is 4.18. And then they said, which gives it in kilojoules per mole. Well, the trick is, what's the moles? Well, the moles comes from the sodium hydroxide. N equals N, little m over big M, which is 1 gram divided by the molar mass of NaOH, which is 40 grams per mole. So this question is quite tricky. It really requires a lot of work, that the moles would be 1 divided by 40. And as a result, you could rewrite that as 1 and 40. Because you're dividing by a fraction, you can multiply by the reciprocal. And so the last piece of the puzzle is to get this in kilojoules. if this is grams, you've got to divide by 1,000 to turn it into kilojoules or kilograms instead of grams and joules. So you're looking for the one that has 1,000 on the bottom, and you're looking for the one that has 40 on the top. So we've got 40 on the top, 1,000 on the bottom. It looks like it's going to be C. This one has 40 on the bottom, and so does that one, so they're wrong. They think you're going to say that because usually you divide by molar mass, but it's just a tricky thing. Because you were dividing by that on the bottom, the 40 actually ends up here. And in this one, it's using the wrong mass. That's quite a challenging question on paper 1 for Q equals MC delta T stuff. That's as hard as it could get. Let's see if we can go on. Okay, a little bit more Hess's law. Again, let's add up to the final equation. 1 on the left, 1 on the left. 2 on the left, 2 on the left, 1 on the right, 1 on the right. So I got minus 390, I got minus 572, and I got positive 890. Okay, my negatives add up to negative 962. My positive is 890, and that's going to give me negative 72. Almost there. Almost there. Is that the last one? 2 more. Okay. A 5-gram sample of a substance is heated from 25 to 35 using 200 joules of energy. What is the specific heat capacity? So a little twist on this equation. They want you to solve for C. They want you to solve for specific heat capacity. So you need to know that that is C. We could rearrange it as Q over M delta T. Q is 200 joules. M is the mass, which is 5. And delta T was 10. So you've got 200 divided by 50, which is 4. So really, you got to know your equation. You got to know what the symbols mean. And then if you do, it's pretty simple math. And finally, one more Hess's law that's a little bit simpler. Okay, we're trying to add up to this last equation. 1 on the left, 1 on the left. I need 1 on the right. I've got 1 on the left, so minus 1, minus 1. So I've got minus 394 and positive 283. That's minus 111. The answer is B. Okay, so if we're going on to paper 2 questions, I asked you to do question 33. All right, using table from the information above, determine the theoretical enthalpy of combustion of methanol. All right, well, forget about entropy. That's an HL concept. Okay, they want you to use standard enthalpies of formation. If you do that, this is the equation that's going to work for you. If you look at the enthalpies of formations of the products minus the enthalpies of formations of the reactants, then you get the delta H for the reaction. So carbon dioxide, they give us a value of minus 394. There's only 1 mole of it, so I can leave it alone. And water is minus 242, but there's 2 waters in the equation, so that has to be multiplied by 2. So that's the energy we get out when we form the products. And if I look at the reactants, methanol is 239, and there's only 1 of it. And the value for water or oxygen is 0 because oxygen is an element, and all elements have formation values of 0. So really, I take minus 394 and 2 times negative 242, and then I add 239 to it because it's minus a minus. And that gives me the delta H for the first one. I'm going to skip past some of the numbers for the sake of time. Now they give you some data here, which is a combustion calorimetry question. So you have initial and final mass of the burner. That's going to be the mass that leads you to your moles, because the amount of fuel that gets burned is providing the heat. The mass of water that you're heating up, that's what goes into your Q equals MC delta T. And we've got a temperature change here of not quite 5 degrees, so we've got 4.9 degrees Celsius. So they want us to calculate the moles. Moles is N equals M over M. So our mass is what? 0.523 grams. We're going to divide that by the molar mass of methanol, which is a carbon, plus 4 hydrogens, which is 16. So it's about 32, if I've done that correct. And that gives us our moles. Okay. Then they say calculate the heat absorbed by the water. So heat absorbed is Q. So they want you to just calculate Q, MC delta T. They do want it in kilojoules, which means we're going to have to at some point divide by 1,000. The mass we were heating up was 20 grams. Divide that by 1,000 makes it our kilogram value. 4.18 is the C value, and the delta T we said was 4.9. Multiply those together, and you get Q. And then they said, determine the enthalpy change in kilojoules per mole. Well, you take the answer you got for Q in part 2, make it negative, and then divide by the answer you got for N in part 1. So this is from part 2, this is from part 1, and that gives you the delta H in kilojoules per mole. Okay? The data booklet value for the enthalpy change of combustion is this. Suggest why this value differs from the values calculated in part A and part B. All right, well, let me get this thing out of my screen. Okay, in part A, I think part A is a sneakier question than part B. So in part A, let's see. I think I've combined wrong questions. The first part, part A, should be quite accurate. Oh, this is very, very subtle. Here it is. Okay. At standard state conditions, when we do things at room temperature, water should be a liquid. And so the fact that they've left water as a gas means that the delta H would be slightly different than it would be if it's a true standard value. That's super sneaky, and I don't think they would ask that on the SL exam. This is an old question that I pulled from the old HL exam. So let's not worry about that one too much. In the second case, though, how would the delta H be different in this part from the literature value? Well, this one came from our calorimetry data, like student calorimetry experiment. And so the major issue in any student calorimetry problem is heat loss to the surroundings. Okay, that's the major issue. You could probably get away with saying incomplete combustion, but the main reason why your answer would be off is heat loss to the surroundings. Okay, so this one was gas phase, not liquid for H2O at standard conditions, which is super sneaky. So don't worry too much about this one, but that one, any calorimetry problem, you should be able to come up with that as the main issue. Okay, here's question 27. This should say table 11 to use bond enthalpies. The value is going to be looking at these bonds. C2H4, there's H2, and here's C2H6. So the bonds broken is 1 C to C, 4 C to H, and 1 H to H. Minus the bonds formed, which is 1 C to C single, and 6 C to H. So if you want to simplify things, you get rid of all 4 of those, and you cut this down to 2. And then you add these bond enthalpy values up, you add these bond enthalpy values up, and you get your delta H. Okay? And now they want you to use, instead of, they want you to use enthalpies of combustion, which are now in table 13, to solve instead. This one's pretty tricky, but what you would do is look up the enthalpy of combustion of each one of these in table 13 and write out the equation, and then do the simultaneous equation method to solve for it. So you'd get C2H4 plus oxygen makes CO2 and water. and you do H2 plus oxygen makes H2O. You'd have to come through and balance these, which would take you a little bit of time. 2 and 2 makes 2, and that makes 3. And C2H6 plus O2 makes. We got 3, we got 4, we got 7. So that means we need 3.5 of these. Okay. Now all these values are in table 13. So for hydrogen, this is negative 286. For ethene, if I can find it, yeah, negative 1411. And for ethane, negative 1561. Those are the enthalpies of combustion. And now they want you to try to solve for that equation up there, which means the simultaneous equation method. So I need 1 on the left, I got 1 on the left. I need 1 on the left, I got 1 on the left. I need 1 on the right, I got to flip this guy. And so this becomes positive 1561, and now you're just adding up those values. So even though it was tricky to come up with that, they told you to go use table 13, and if you're kind of stuck, the best thing to do is write out the equations that represent combustion. You write down the values, and you can solve using simultaneous equation. Now they want to know, why is the first answer less accurate than the second answer? Well, the first answer was bond enthalpies, and the key issue with bond enthalpies is they are average values. They're not specific to this reaction, whereas the combustion values are very specific to the reactions or the reactants involved. The next question is, use bond enthalpies to deduce the value for this. Well, this is rather tricky, and again, I think this is an old HL question that I adapted. What they'd want you to see is that the change is really that you're still doing the same thing as the first one. So they're equal to part A, the first part of the question, where you calculated with bond enthalpies. You're breaking the exact same bonds, which is 1 C to C and 1 H to H, and then you're forming 1 C to C and 2 new C to H bonds. And so since you're breaking and forming the same bonds, you should have the same delta H. I wouldn't worry too much about that. I don't think that would be asked on the SL exam. But then they do ask, they say that there's more error, if you read this quickly, there's more error when you do bond enthalpies for this reaction than there for the first reaction. And so what they want you to see here is that you're in the liquid phase. And since bond enthalpies are only measured in the gas phase, this leads to more error than even the first bond enthalpy answer. And you would need to know information about, what does it take to go from liquid to gas? What's the delta H associated to go from liquid to gas? And that would be the missing piece. Some of that I really don't think they'd get into so much, but again, it's just a question about what are the limitations of bond enthalpies. So that was a fast-paced video. I hope it helped you review your homework questions, and we can talk about any other questions in class.